Hello everyone! In this video we're going to talk about limits at infinity. So limits at infinity are limits where you find out as x approaches infinity, what does the function represent. So let's talk about the difference between a limit at infinity and an infinite limit, which sound similar and are actually a bit related, but they're two different things. So I'm going to draw two functions, okay? So let's call this C. Let's call this C. Okay? So here in an infinite limit, which we did last episode, which allowed you to find a vertical asymptote, as a function approaches a value, as x approaches a value, f of x approaches infinity, or negative infinity. Okay? So here it approaches infinity as the function approaches a value. In limit at infinity, as x approaches infinity, okay, you start to see the function start to approach C, or any integer. F of x approaches C. Okay? And these are horizontal asymptotes. Horizontal asymptotes. So you can start to see a little parallel as a function for vertical asymptotes, as a function approaches a value, as x approaches a value, the function approaches infinity. However, what we're doing today, as x approaches infinity, the function approaches a value. And these are limits at infinity. Limit as x approaches infinity of f of x can be also equal to plus or minus infinity, or any integer c. Okay? So like for a line, as x approaches infinity, f of x will also approach infinity, because it will just keep on increasing without bound as x increases without bound. Okay? So let's do a couple of examples, okay? Just built on the fact. And before we do those examples, let's learn an important fact. That the limit as x approaches infinity of 1, or it could be any integer a, over x to any power will always be 0. Why? Because a is a finite integer. However, as x increases without bound, the numerator starts to become insignificant. The numerator starts to become insignificant compared to the denominator. And as you divide by higher and higher and higher values, the answer will become smaller and smaller and smaller, and it will approach 0. So as x approaches infinity, as x increases without bound, this entire expression will approach 0. And it's very useful to help us evaluate certain functions. So let's do this. The limit as x approaches infinity of phi plus 3 over x squared. Okay, so if you want to find phi plus the limit as x approaches infinity of phi plus 3 over x squared, well, you can break it up. This is a constant, okay? So even as x changes, since it's a constant, the limit of a constant is always equal to that same constant. So phi plus 3 over x squared. Remember, as x becomes infinitely large, the denominator will become infinitely larger than the numerator. So the expression will approach 0. So 5 plus 0 equals 5. However, there are limits that are not as simple as these. Usually limits are not as simple as these. Okay, so start another one. Let's find the limit as x approaches infinity. The 3x squared plus 4x divided by 2x minus 5. So now we have a rational function. Okay, so we have a rational function. And we need to get a way so that it becomes some number a divided by x to some power. Because then we could just replace it by 0. Since I said before, as x approaches infinity, this expression, we know for sure, will approach 0. So what we can do is divide by the highest power in the entire expression. That'll be x squared. That'll be x squared. So we get 3 plus 4 over x. X divided by x squared, it just equals x to negative 1, or over x. We get 2 over x minus 5 over x squared. You can replace these all with 3 plus 0 over 0 minus 0. So that's 3 over 0. So it will approach infinity. Okay, the limit does not approach a value. So the limit does not exist. It just goes to infinity. Okay? However, let's do the exact same problem except with a little change. We're going to do a similar problem. The limit as x approaches infinity of 3x squared plus 4x over 2x squared minus 5. Now, we want to divide by the highest power in the entire expression. Okay? So we're going to divide by x squared. Okay, all of it. We're going to divide every single term by x squared to keep it equal. So we have 3 plus 4 over x over 2 minus 5 over x squared. And now we can easily evaluate this limit, because the limit as x approaches infinity of 4 over x and 5 over x squared is 0. So we get 3 over 2. So we've changed it from a limit approaching infinity to a limit approaching a finite value, 3 over 2. Okay? So if we had a limit, let's do this one more time, a similar problem to the first two, 3x squared plus 4x over 2x cubed minus 5. Well, we want to divide by the highest power in the whole expression. So the highest power is not x squared, but it's x cubed in the denominator. Okay? So we have 3 over x. And you might see where this is going. 4 over x squared over 2 minus 5 over x cubed. And what does that result in? Well, we get 0 plus 0 over 2 minus 0, which equals 0. And you can see a trend here. If the highest exponents, the first terms, have the same degree, the polynomials on the top and the bottom, if they have the same degree, if the highest exponent is the same, they'll approach a finite value. If the top exponent, the top highest exponent, is one larger, or just even larger in general than the bottom one, it will approach infinity. Otherwise, if it was the opposite, the bottom exponent is larger than the top one, it will approach 0. Okay? Now, there are some cases where you have to approach negative infinity. Negative infinity. However, the case is pretty much the same, because negative infinity, okay, regardless of 1 over x, for example, negative infinity will just be negative 1, okay, over infinity. Okay, which is negative 0, which is just 0. So even if a limit approaches negative infinity, they'll more or less be the same to a limit as x approaches positive infinity. The reason why I say more or less is because there are times where the limits as x approaches infinity and negative infinity are not the same. So let's look at this one. This one is a little trickier because now I'm going to add exponents. Sorry, not exponents, radicals. Okay, so 3x plus 5 over the square root of 2x squared minus 6x. Okay, so this limit, okay, this limit is a bit trickier to evaluate because you have a radical expression. However, you want to divide by the highest power, okay? You might be tempted to say x squared, but x squared is inside of a radical, okay? So you can't really divide by x squared. What you can divide by is x, okay? And because you know that x is equal to the positive square root of x squared, okay? Because x is approaching infinity. Okay, so forgive that. So we can apply the substitution that x equals the square root of x squared. Might be tempted to say that there's also a negative square root of x squared, but this is where the difference comes in as x approaches infinity and x approaches negative infinity. Okay, so we're going to divide each side by x. Okay, so we're going to divide the top by x, but the bottom by square root of x squared. So we can get inside that radical. We can get inside the radical, and we get 3 plus 5 over x over square root of 2 minus 6 over x squared. Sorry, 6 over x. Okay, and as x approaches infinity, x becomes larger and larger and larger and gets 3 over the square root of 2. Okay, so let's evaluate the same limit as x approaches negative infinity. So 3x plus 5 over square root of 2x squared minus 6x. Okay, so as x approaches negative infinity, okay, x will start to become negative. Okay, so x will start to become negative. So you can apply the substitution negative x squared over the negative square root of 2x squared minus 6x over x squared. And now we get 3 plus 5 over x. We pulled the negative outside because negative square root of x squared divided by the square root of 2x squared minus 6x, you can choose to pull out the negative and just put it outside over here. You can take this outside. Okay, so that becomes the square root, negative square root of 2 minus 6 over x. So now we get negative 3 over root 2. So we got a negative answer with a radical in it. So that is an important exception that to the rule that the limits as x approaches infinity and negative infinity will be the same. Another important exception will be for a real line. Okay? For some functions, notably odd functions, that are symmetric to the origin rather than to the x-axis, the limits to infinity and negative infinity will be the opposites of each other. Okay? However, so this It will approach negative infinity. This will approach infinity. And what's useful about limits at infinity is that you can use them to find horizontal asymptotes, which will be a useful feature as we go later on in this course.